Math 2414 volumes. Volume of a solid of revolution rotating around other axes, example 1. And yes, this is the correct spelling of the plural of axis, axes. On the board, we've got a lamina that we've seen already. A lamina bounded below by y equals the square root of x, bounded on the left by the y-axis, also called x equals 0, and bounded above by the horizontal line y equals 2. But this time we're going to rotate it around a different axis of rotation. We're actually going to rotate it around its upper boundary, around the horizontal line y equals 2. Now the good news is the axis of rotation is a boundary for the lamina, which means when we rotate it around there, we're not going to have any holes. This won't be the washer method, this will be the disc method. But the problem is, how are we going to find the volume of its cross-section? Keep it along the lines of, take a cut perpendicular to the axis of rotation. If we're going to cut this perpendicular to y equals 2, then we're still going to hit the x-axis at some point, so keep that in mind. If we were to take this little sliver and rotate it, we would get a disc. And the area of that disc is going to be pi times the radius squared. The radius would be right here. But where in that picture would I put the R? As if it weren't obvious because I just changed it to green. That radius represents this length here. So this is going to be a little bit trickier to answer the question, what is the radius as a function of x? Because remember, we want our cross-section area as a function of x, and it's currently a function of r. So how are we going to pull that off? Well, in order to pull that off, we need to find an ordered pair that somehow involves the r. Well, where is it? The problem with this r is it doesn't represent a displacement from the x or y axis. X-coordinate, displacement along the x-axis, distance from the y. Y-coordinate, displacement along the y-axis, distance from the x-axis. So it looks like we're stuck because I can't set up an ordered pair where neither the x nor y, where either the x or y is this radius because it's not measuring a distance from either axis. So what do? The answer is we embed it in something that does represent a distance from the x or the y-axis. Since this r is representing a vertical displacement, we need to embed it in something that represents a vertical displacement from the x-axis. In other words, I'm going to fill in this gap. Now, what should we call that gap? Well, it doesn't really have a specific meaning here. It just represents a vertical displacement from the x-axis. Well, what do we normally call something that measures how far up you go? Y. So how's that going to help us? Because now I know something about how y and r are related. Because together, how far up do they go? Together they add up to give 2. So from this picture, we can see that the radius that we want plus that y is equal to 2. Now, how's that going to help us? Well, notice that we're using a point here on that parabola. It is a parabola, it's just going sideways. In this picture, what would we label that coordinate, those coordinates? Well, it's over x and up y, so I think x comma y is a good ordered pair for it. And, hold on, I'm getting ahead of myself. I'm going to write that again, but I wish I could have not said it first because I want to go back to this. Excuse me. We're trying to get our area as a function of x. It's currently a function of r. This equation that we formed by filling in this missing piece and calling it y. Gives us a relationship between r and y. If we solve this for r, we're going to get r equals 2 minus y. And although there's nothing wrong with that, it doesn't accomplish what we want. We want r as a function of x, not as a function of y. Let's go ahead and put that back up here for a second. Pi times 2 minus y squared. Still not what we want. We want the area as a function of x, but now it's a function of y. But now we can ask the question, what's the relationship between x and y at this point? Because this point contains both the x and the y in this picture in an ordered pair. Well, this ordered pair is on the graph of y equals the square root of x. So what we know is y is equal to the square root of x. That's the relationship between the x and y being an ordered pair on this graph. Well, because y equals the square root of x, that means I can take out the y and replace it with the square root of x. So it's a little bit ugly, but it's the right expression. When you rotate around a different axis, you have to dance around it really carefully, because a piece of the lambda will represent the radius that you want for your formula, but that radius will not directly be a coordinate of an ordered pair. So you find an ordered pair that touches the radius, and then introduce, in this case, a third variable y, and make an observation like, well, when I add these, I get 2, so if I subtract, I get r equals 2 minus y, but on this ordered pair, y is equal to the square root of x. But I think I have it. I think I got what I want. I've got the area as a function of x, and I know the limits of integration. On the bottom of this lambda, well, remember this is a dy problem. No. This is not a dy problem, it's a dx problem. The leftmost part of the lambda, x is equal to 0. What is x equal to over here at the right hand? Well, I know y equals 2, and on this parabola, I know that y is equal to the square root of x. So if I put a 2 here for the y and solve, I would get x equals 4. In other words, this point is 4 comma 2, which is pretty easy to see at this point, because the square root of 4 is 2. So my x's are going from 0 to 4. This is my area, so now my volume is going to be the integral from 0 to 4 of that guy. Pi times 2 minus the square root of x squared, dx. And now it's calculus 1 problem. So how do we do this calculus 1 problem? If you're thinking use substitution, think again, because there wouldn't be enough for the du package. However, we can square this binomial. And let's go ahead and pull out the pi. It's not going to do anything. It's just going to sit there. We can write this out twice and FOIL it. If we did, we would get 2 squared, which is 4, minus this product twice, so minus 2 of this product, so minus 4 squared of x. And then plus this squared, which would be plus x. If you can't just see that full result, then you need to work it out and convince yourself that that's what it is. But this is a pretty easy thing to integrate. As long as you remember that we don't integrate radicals, we integrate their power equivalents. So instead of 4 squared of x, it'd be 4x to the 1/2. And now we go to town. Antiderivative of 4 is 4x. I'll come back to this guy in a second. Antiderivative of x is 1/2 x squared. For the middle term, we would raise the power by 1, which would make it 3/2, and then multiply by its reciprocal, so multiply by 2/3. But 2/3 times 4 is 8/3. And this is going from 0 to 4. 0 does annihilate the antiderivative. As a lower limit, we can ignore it. Only if it makes it equal to 0. There are things that 0 doesn't turn into 0, like cosine, or e to the x. Cosine of 0 is 1, e to the 0 is 1. So don't just always assume, I can ignore that. Only if it makes this equal to 0. If we put in 4, 4 times 4 is 16, minus, we'll come back to this in a second. 1/2 of 4 squared, 4 squared is 16, 1/2 of 16 is 8. All right, for this guy, 3/2 power means cube and square root. So if we put the 4 here and square root it, the square root of 4 is 2. 2 to the 3rd power is 8. 8 times 8/3 is 64/3. And again, if you need to take more time to do the arithmetic, that's what you do. But this video will go on forever if I go through every little detail, although sometimes I feel like I do. Common denominator is 3. 64 is already over 3. If I triple this, I get 48 over 3 for the 16. If I triple this, I get 24 over 3 for the 8. And now I just got to put everything together. Let's see, 48 and 24 is 60, 72. 72 minus 64 is 8. So we get an 8 on top, a 3 on the bottom, and a pi, and it's over. You may be wondering, is there a way to generalize this approach where you have a disk method, but it's around a different axis? The answer is kind of, but unfortunately, there's so many variations on this theme that I've always just found it's better to draw a segment representing the radius, draw another segment connecting it to the radius but taking you to an axis, x-axis or y-axis, establish that relationship, and then get what you want.